lecture number 3. And today we will discuss global existence. Global existence of solutions. I'd like to recall that we discussed the initial value problem. The vector equation, this is the vector equation, x prime equals f of t, x of t. And the initial conditions will be x at the point t0 equals x0. This is the initial value problem. So f is a function defined in D, and it goes to Rn. It maps the set D to Rn. D is a subset of the product R times Rn. So the variable t is time. So this equation can be considered as the dependence of the coordinate x. So it is a vector, right? And components, right? T is time, and this is some law, maybe how the derivative depends on, so is the function depending on t and x of t. So t belongs to, is in R, and the vector is from Rn. D is some open set. Okay. F is also a vector function. Okay. And we assume that F is continuous and locally Lipschitz. In X. In what follows, I will often omit the bar above the variable. Okay, so in X, in D. If F is continuous and locally Lipschitz in X, in D, then we know that theorem, Picard-Lindelof theorem, holds. So, Picard, just a moment, I will try to find the spelling of Picard. Just a moment. I'll have a look. Picard, Lindelof, I think so. This, but maybe I need some. Maybe I have lost. Right. It's okay. I'm right. Picard-Lindelof theorem that under this condition, if F is continuous and locally Lipschitz in X and D, then for any initial value, t0 and x in D, there exists some interval, I will call it Ix, I sub x, containing t0. Okay, and so exists some interval okay, let it be x from Ix qRn, which is unique. So this solution and this solution is unique. Right. So under this assumption, right, for any point there exists an interval and a solution, and this solution is unique. So this means that, for example, if this is R, and we have some set D, open set D, and a point, we fix point t0 and x0 bar, so the vector. And there is an interval, so this is an interval. And a solution which is unique in this interval. This means that if there is another solution from Ix to Rn, then these two solutions coincide. Right, so we will use this in what follows. This is very important theorem, and today we will consider applications of this theorem, and we will move further. We will discuss global existence. Right. And now we will start with the maximal interval of existence, so the maximal interval of solution. This will be, I will use that space, I think. I will state and prove the following theorem. This theorem, will be the extension and maybe the application of this Picard-Lindelof theorem. Okay. So the beginning will be the same for all the statements today. This will be the beginning of all the theorems. Assume that F is continuous and local ellipses in X and D. D is an open set. It is a subset of Rn plus 1. It should be open. And F is continuous and local ellipses. So we will consider only the functions which are continuous and local ellipses in X and D. Well, so under these assumptions, okay, so maybe I will call this, let it be asterisk, right? If this is true, then there exists the interval AB containing T0 and a solution to the initial value problem. Let it be equation number 1, a solution to 1 to the initial value problem. We will call it phi of t from AB to Rn such that such that for any other solution x of so x from Ix to Rn of the same problem of 1. Okay, so there exists an interval, so this will be the maximal interval, right? But we know by Picard-Lindelof theorem, we know that there exists some interval Ix and a unique solution x, right? But for any other solution, we may choose any interval, any possible interval, right? And any solution. But for any other solution of the same initial value problem, we have the following. Ix must be a subset of AB. So AB will be a maximal interval. So theorem states that there exists a maximal interval AB. Subset. Solution to solution, right? So this means solution phi to the initial value. Right, so we should switch the positions, I think. Let it be, so I will improve. I think that it is not correct. Thank you. Solution phi from AB to Rn of the initial value problem 1, such that for any other solution of the same problem, we have that the interval is a subset of AB and x coincides with phi x of t. So for just a moment, x of t coincides with phi of t for any t in Ix. So these two solutions coincide on this interval Ix. So this is the statement. And I will prove it. It is not, the proof is not very difficult. So I will start the proof here. First of all, I will define this interval. Okay, maybe let it be AB is called under the assumption of this theorem, AB is called the maximal interval. Of solution X. X of t. So maximal interval. Well, let's prove this. So first of all, I'd like to define AB. I will consider all possible intervals. Right, so I will do, maybe I will try to sketch the figure. Let's fix the point t0, x0. Let's fix the initial value. And let's consider all the intervals containing t0 on which there exists a solution to this initial value problem. So this should be inside D. D is an open set. So I may consider all possible intervals. For example, this interval, then this will be the second interval, right? So different intervals. And I will take the union of all possible intervals for all solutions X over all the solutions. Right. Now, first of all, let's discuss why is it an interval? Maybe, so if we take the union of all possible intervals containing t0, whether this object is an interval or not Is it true that this is an interval? First of all, the question is it open? AB, so okay, so first of all, don't look at this AB. So let's consider this object. Is it true that this object, this union is open? Given that all the intervals Ix are open, right? So the union of open sets, many number, maybe finite or infinite number of open sets is open, right? So this is an open set. Is it connected? So any interval Ix is some interval from alpha to beta, maybe. So this is an interval. It is open connected set. What about the union? Open and connected. Is it connected or not? So any 2 points can be joined by some segment. So this is the right. So T0 connects. So just a moment. So that connected means any 2 points can be connected, can be joined by some continuous curve, right? But so here we live on R1, right? So on the real line, and so by the connected set, we mean the interval, just an interval, right? Okay, so any 2 points can be connected via T0, and so this union is connected, and it follows that this is an interval from A to B. So yes, we can define AB in this manner, and after this, let's define phi. Next, we need to define phi, the function phi, this one. We will do the following. So let what is f of t for some t? Given t, what is phi of t? So to define this, we should find Ix interval from this set, right? Ix containing this value t. T is different from T0. So this means the following. Okay, so we have several different intervals. So Ix1 maybe, Ix2, and so on. So we consider the union of all the intervals. We will get the interval from A to B as the union of these intervals. This point is fixed. This will be AB. Okay. Given any point T, let's define a solution. So to do this, we should, so T belongs to one of the intervals. And so we should find this interval containing T. Find the solution, the corresponding solution, because this interval corresponds to some solution, x of t of the initial value problem. And after this, we set f of t equals x of t. Okay, so we have defined AB and phi of t. What shall we do next? Is it true that this completes the proof? Is it true that the theorem is proved? No, why? So what's the problem? We should prove, so we have defined. We should prove that phi of t is well defined. this means the following. So look here, and so this is of course well defined. This part is well defined. Difficult.
Not easy.
Not easy, right? I see. So this is well defined. But what about phi of t? It should be unique in some sense, right? It should be unique. It should be. So this is a function. It should be defined. So we take t. We have found an interval containing t, but maybe there are two intervals, right? So the union, you can see the union. Look at the at this figure. So for some t, maybe we take this t. It belongs to two intervals, this interval and this interval, right? Or so I have colored chalks. Well, maybe I will not green. Maybe so. This is the interval number 1, and this is the interval number 2. And if we consider this t, it belongs to two different intervals. And so we have two different solutions. It will be, so for example, x of t and y of t. Right? Different solutions. They have the common point, right? Because these are two solutions of the same initial value problem. And we know that locally, Picard-Lindelof theorem guarantees that locally they coincide. But what about two intervals we can't compare? Maybe they coincide locally, and if we move aside from this point, far from this point, this will be not the case, will not be the case, right? Possibly this may happen. And so we should prove that phi of t is well defined. Okay, so suppose for some t, we have two intervals. T belongs to Ix, and x of t is a solution. And t is in Iy, and y of t is also a solution. And we need to prove that, so we want to prove x of t equals y of t. Okay, we know that locally these two solutions coincide because of the existence and uniqueness theorem, right? Locally that they coincide. And okay, let I be an interval on which, so where x of t equals y of t. And we know that t0 is in I. So locally they coincide. But maybe I is not the same as the intersection of two intervals. So we want to prove that these two solutions coincide on the intersection of two intervals. So we want to show equals the intersection. Okay, suppose not. Assume the contrary. This is not the case, so I is a subset and consider, so I is an interval, some interval, it is raised from the existence and uniqueness theorem. So this is the interval from Picard-Lindelof theorem, the interval on which the solution is unique. If I is a subset, is a proper subset, if it doesn't coincide with this intersection, then there exists the endpoint of I. So I maybe equals from alpha, the interval from alpha to beta, and suppose B is in intersection. Suppose beta doesn't coincide with the endpoints, an endpoint of this intervals, right? So beta is somewhere here. This is beta, and it is different from the endpoints. So this is beta. Well, and this is the endpoint of IY, and this is IX. And beta is inside IX. Right. Well, so two solutions are the same on this interval. So these are two continuous functions. X of t and y of t are continuous. And they must be differentiable, so they are continuous. And we may consider the limits x of t as t approaches the endpoint beta from the left is the same as, so these two solutions coincide on I, and so we can take the limits as t approaches beta. Call this point B by P. Let it be P, and consider an initial value problem. Initial value problem, which looks like x prime equals f of t x t, and x of beta equals p. So we will consider the initial value problem with this beta and this point p. By Picard-Lindelof theorem locally, so there is an open interval containing beta on which the functions are the same. Picard-Lindelof theorem. There exists an interval containing beta. Let it be beta minus epsilon, beta plus epsilon. On which x of t equals y of t. And so this is a contradiction with our assumption that beta is an endpoint. So I was an interval on which x of t and y of t are the same. Beta was the endpoint. So we assumed that I is a proper subset of this intersection. So I is less than this intersection. It is inside this intersection. But we came to the contradiction. So we extended these two solutions to the point t equals beta and applied Picard-Lindelof theorem to this initial value problem. And so we can see that two solutions must coincide on beta minus epsilon, beta plus epsilon. So they must coincide on this interval. And so this is a contradiction with the fact, with our assumption that beta is an endpoint, right? So since we came to the contradiction, then we have proved that I is equal to this intersection. And so 5t is well defined. So now this completes our theorem. So the theorem is proved. Well, all right. Now let's go further. So I have defined a maximal interval. It comes from the statement of our theorem. So AB is called the maximal interval of the solution. Well, and let's consider an example now. So it's time to consider an example. We will consider an initial value problem of the form simplify x prime equals x squared and x of t0 equals x0 with arbitrary values of t0 and x0. Let's find a maximal interval for this initial value problem. So first of all, the first question, what is D? What is D? D should be a domain on which f is continuous and locally Lipschitz. Continuous and locally Lipschitz. Look at this function. Okay, what is the dimension of D? First of all, is the subset of R times R, right? This is the dimension for T and for X, right? So D is in R2, and we should find the domain on which this function, this is f, it must be continuous and locally Lipschitz. Is it continuous? X squared, is this a continuous function? And is it locally Lipschitz? Locally Lipschitz? Okay. Right, check. How to check this? So we have discussed on the preceding lecture that if the function is of class C1, so if f is C1 function, is of class C1, this means that it is differentiable, that it has a continuous derivative or continuous partial derivatives if it is n-dimensional, but now it is one-dimensional, so it must have a continuous derivative. If f is C1, then it is locally Lipschitz. So this function is differentiable, right? The derivative is equal to 2x. This function is continuous, so this function is C1, right? Clear? So it is C1, and so it is locally Lipschitz. So in practice, it is so often it is very easy to check whether or not the function is locally Lipschitz. So if it is differentiable, if it has continuous partial derivatives, then it is locally Lipschitz. Sometimes we consider the converse statement is not true. So if the function is locally Lipschitz, it need not be C1. But usually we deal with C1 functions, so it is not difficult. Right, C1 and locally Lipschitz, and so we may take D equal, so D is R2. R2. We may consider this domain R2 because everywhere this function is continuous and locally ellipses. Right. And now let's discuss the maximal interval. And after this we will have a break, right? Let's finish this example. We can solve this problem, right? The variables are separated, and so we can solve it, and it will be this. Then integrate both parts. So except for, so x identical 0 is of course a solution, right? It is lost by dividing by x squared, but we should consider it. So this is a solution, but to obtain this solution we need, what about t0 and x0? X0 must be taken to be equal to 0, right? So if x0 is 0, right? For any t0, t0 is an arbitrary, but if x0 is 0, then we have this. But if not, then we should divide by x squared and integrate both parts. We will get minus 1 over x equals t plus the constant, and x equals minus okay, that is the minus c 1 over c minus t. Okay, let's consider integral curves. T, x, what are integral curves? So here we have an asymptote, t equals c, somewhere here c, and then we have hyperbolas. And if we change, if c is varied, then we have the set of hyperbolas. Okay, and what about the maximal interval? If we have if we fix t0 and x0, what is the maximal interval of this solution? No, this is not true. Look at this curve. From minus infinity to some constant c. How to find? So we need to find c. How to find c?
When the curve is fully like line straight.
So first of all, we need to find c. We should substitute t0 for t and x0 for x and solve this equation, right? It will be, so let's solve it. From which we have c, let's find c. C will be equal to 1 over x0 plus t0. This is c, and this is the end point of the maximal interval. So the answer is, if x0 is 0, then x is identical 0, and the maximal interval will be from minus infinity to plus infinity, right? From negative infinity to positive infinity. If x0 is greater than 0, then the maximal interval will be from negative infinity to c, so to 1 over x0 plus t0. Right, clear? From negative infinity to c, to this point, we have found c. So given an initial value, we can find c and substitute it here. Oh, well, and if x0 is less than 0, then the interval will be, so for negative, if x0 to 0, x0 is negative, then the interval starts from c to positive infinity, right? So from 1 over x0 plus t0 to positive infinity. So this is the answer. Now let's stop here. Let's have a break. The next theorem, I will state it without proof, but we will use it. So theorem number 2. Okay, so f, as before, f is continuous and locally ellipses. In D, if f is continuous and locally ellipses in D. So again, we consider the initial value problem. So we consider a solution with a maximal interval. Okay, so just a moment. And x of t is a solution of this initial value problem, is a solution with maximal interval AB. Okay, then x of t leaves any compact set. K contained in D as t approaches A and as t approaches B. So I think I need to explain this. I will omit the proof, and I have chosen the most maybe so the easiest statement, right? It can be formulated, it can be stated in more complicated form, but leaves any compact. What does it mean? So now I will explain the meaning of this theorem. So suppose we have a domain D, so the set D. We have an initial value problem, t0 and x0. And if we consider any compact set, for example, this one, then a solution must leave this compact set as t approaches A and as t approaches B. If A is so okay, so as t approaches A and t approaches B, this means that our integral curve intersects the boundaries of this compact set, right? This is K. Okay, so in this manner. This is A, and now what is B? Well, B may be somewhere here. So leaves any compact set. So if we start at this point and goes along the integral curve, we must leave. So this theorem guarantees that we leave this compact set, or goes to the boundary of this, or we go to the boundary, we come to the boundary of this compact set. What is compact set? Do you remember the definition of the compact set? Closed and bounded. Bounded and closed and bounded set, right? Compact. but this is true in Rn. So if our metric space is n-dimensional, then this is true. But the definition of the compact set, sometimes it is given, so sometimes it is different from this. This is a criterion of a compact set. But the definition, usually the definition is given in the form of the cover. So we consider any open cover of this compact set, or maybe, so have you heard anything about a cover? And no, and we there is a finite subcover of any open cover of the compact set. So if not, so I will not mention it, right? So let it be the definition. So compact set is the same as the closed and bounded set in in Rn, but we are in Rn. Well, so this is let's look. Let's consider. Let's apply this theorem to our example. In our example, let's consider any compact set, any you want. So maybe we may. It must be closed and bounded. It may be a rectangle, for example, this one. Right. And you can see that our trajectory, our solution leaves this set at this point and then this point. If t approaches minus infinity, negative infinity, then these points are outside of this compact set, right? The trajectory leaves our compact set as t approaches negative infinity, and it leaves our compact set as t approaches c, right? Is it clear? Understandable, I think, right? Or we may consider this rectangle, any compact set in D, and so we can. So if we consider this rectangle, then our theorem also guarantees that we'll leave out the trajectory leaves this compact set as well. So leaves the upper boundary here at this point and leaves the left-hand side, so this boundary at this point, right? So that the trajectory leaves the compact set. Okay, let's try to apply this theorem for finding. So in some task, we will try to find the maximal integral, the maximal interval using this theorem. We will consider a vector equation, example 2. We will consider the following. X. Well, so this is a system of differential equations, or this can be considered as one vector equation, one vector differential equation, right? And sometimes I will speak about the system, so I will consider a system as one vector equation. Right, let's discuss it. Okay, so let's consider any initial value problem. So let's fix t0 and x0. X0, y0. We have 3 variables. T is time, and x and y are 2 variables, right? This is an independent variable. T is an independent variable, and x and y are 2 dependent variables. Right? So let's fix it. And suppose, okay, suppose AB is a maximal interval. T is an AB, a maximal interval. Well, now I want to show that B is positive infinity. So B is infinity. Why? So first of all, I'd like to rewrite. I want to rewrite these equations in the polar form, in polar coordinates. So I will introduce two polar coordinates, the radius and the angle. X equals r times cos phi, or maybe theta, let it be theta, and y is r times sine theta. And let's try to rewrite these equations in the polar form. So what is x prime? Let's differentiate this. It will be r prime times cos theta plus r times sine, so minus r sine theta times theta prime. It's x prime, and it should be equal to minus x minus 2y. So equals minus r cos theta minus 2r sine theta. And for y prime, we have r prime sine theta plus r cos theta times theta prime equals minus r sine theta plus 2r cos theta.
I have a question. What's the reason that we assign for x and y cos theta and sine theta? What's the reason for that?
The reason for this for the introduction of polar coordinates. So just wait. In terms of polar coordinates, this equation will be so that the form of these equations will be more easy, and we will be able to solve them, right, or to discuss them, right? Okay, so let's try to find r prime from these simultaneous equations. So I want to eliminate, first I want to eliminate theta prime. To do this, I want to multiply the first equation by cos theta, and the second one by sine theta, and add them together. And I will get the following. R prime times cos squared theta plus sine squared theta equals, so theta prime will be eliminated. Is it clear? If we multiply this by cos theta and this by sine theta and add them together, so theta prime will be eliminated. It will be multiplied by 0. Is it clear?
Yeah. Okay, yes.
Right. Next, move further. So multiply this by cos theta, this by sine theta, and add together, and we will get minus r times cos squared theta plus sine squared theta. And these two terms will also be eliminated. This multiplied by cos, and this is multiplied by sine. So look at this equation. So this implies that r prime is equal to minus r. This is the first equation, right? It's much more easy than these equations. Next, I want to eliminate r prime. To do this, I will multiply by what? So next, I will multiply the first equation by minus sine theta, I think, and multiply the second one by cos theta, right? And this will eliminate r prime, and we will have, so the result will be theta prime equals so r times theta prime, right? R times theta prime equals what? Sine will be this, so sine 2 r. Clear? And this is the same as we can divide by r, and we get the following. R prime is minus r, and theta prime is 2. So these equations can be solved separately, right? So we can solve the first equation, this one.
How did you get r times theta prime equals to r?
Here, so what's the problem?
How did you arrive at that?
This, so how have I obtained this, right? Okay, so if we multiply the first equation by minus sine theta and the second one by cos theta and add them together, then r prime will be, the coefficient of r prime will be 0, because this is multiplied by sine and this is by cosine, right? And added together. So this coefficient will be r times sine squared plus cos squared. So this. Then this will be eliminated because this is multiplied by minus sine. So cos sine and sine cos with the inverse sine, right? With the sine minus. So, right.
1 for x prime, you said equals to r prime. How come if x is equals to r multiplied by cos theta, how do we get to r prime? Like x theta x prime.
X prime, right?
Equals to r prime multiplied by cos theta.
So differentiate this, right? So to find the derivative of x, we need to differentiate the product rule, just product rule. Well, next I divide by r and get this, and so we can solve these two equations separately. So to solve the first, we will do the following: dr. We can separate variables. So ln r is positive, minus t plus c. So r equals constant. So r equals c1 times e to the power minus t, and theta equals 2t plus c2. Okay. Okay, so from the first equation, we can see that as t approaches positive infinity, then r decreases, right? As t approaches positive infinity, look at the power. So c1 is constant multiplied by e to the power minus t. If t approaches positive infinity, this approaches 0, and so r approaches 0. This means that, look at the plane xy, given any initial point t0, x0, y0, let it be here, somewhere here, right? x0, y0, and for t, we have this axis for t. So in what follows, I will draw this figure in 3D. I will try to draw it in 3D, but now this is the plane figure. We start from x0, y0. And from this, we can see that theta is 2t and c1 is, r is c1 times this. So this means that r approaches 0 and theta varies as 2t plus c2, so something like this. In 3D, it will be, if we have, so suppose this is the plane, xy plane. And this is time. So we start with this point, and next we have a spiral. Which approaches spiral around t-axis. So it is a two-dimensional figure, and this is three-dimensional. Now we live in dimension 3, right? We have three variables, an independent variable t and two dependent variables t, x and y. And so this is a 3D figure. So we start from this, and this is a projection of this spiral. Projection, this is a spiral also, but this is a projection of this, right? So we move to, and our trajectory becomes closer and closer to t-axis. It approaches t-axis as t approaches infinity, right? This spiral. Right. And so what about the application of theorem number 2? How to apply it? Right. So we have let's consider any compact set. So suppose we are in the so let it be AB. So let's consider the product. Let it be just a moment. CD. Some two finite numbers and the direct product with the closed ball centered at the origin with radius r, some fixed radius r. So I can draw this compact set here in 3D. This will be so the ball multiplied by the segment. I will use colored chalk, right? Okay, so the compact set will be, so this is the ball of radius r. This is the time period from C to D. By theorem 2, we know that our trajectory must leave this compact set, right? But if we take a radius to be large enough, then we can see that that the radius is increasing. It so it is decreasing. It decreases as t approaches infinity. So we can't intersect the lateral surface of this cylinder, right? So this is a compact set, but since radius is decreasing, then we can't intersect this lateral surface, right? And therefore we must intersect this wall, right? So this fact proves that so since this is true for any value of d, then the maximal interval must be, so b must be positive infinity, right? So we can extend our trajectory, our solution to any value of t, since we intersect this, the base of the cylinder, right? This wall. Okay. Well, so this is only example number 2 and theorem 2, but we should consider. All right. So now we should discuss global existence. So global existence theorem.
It should leave the compact set closely, right?
Right, but we don't know. So we start with. But so if we go that way, so the radius is increased, and so so if we consider this cylinder, we can elongate this, right? We can consider d larger and larger, right? We may move d to the right.
Yeah, but that's just one side of the interval. What about the other side? What
C. What about C, right?
Yeah.
What about C? What about A, maybe? A, right? Is it infinity? So the answer is A is negative infinity, but we can't prove this using only theorem number 2. We need to know theorem number 3. So now I will state and try to prove theorem number 3. And after this, we will be able to prove that A is negative infinity. Right. So under above assumptions, so the same assumption, the same initial value problem, f is continuous and local ellipses. Then I will state theorem number 3. If D is the product of I times times Rn, I is an interval, and if for any t from the interval, we have the following. Our function, in just a moment, so I will recall the initial value problem. Okay, so this is our initial value problem. And if this function, the norm of this function, f of t, x of t, is less than or equal to some constant a depending of t times the norm of x of t plus b of t, where a of t and b of t are non-negative, continuous functions. Okay. Okay, then on I, the solution, the initial value problem, this one, has a unique solution. Okay, so if f satisfies this inequality, then the maximal interval is at least I, right? So I is included in the maximal interval. If this is true for the entire real line, then the maximal interval is the entire real line. Right? So if we go back to this example, we can see that the function is linear. So this assumption is satisfied for this function. So we can see maybe I will do the following. I will try to, maybe I will not prove then. I will not prove the theorem then. I will show how it can be applied in this example. Let's apply it here. Let's check this inequality. I claim that on R2, our vector function, so the norm of f is less than or equal to a times the norm of x plus b. Let's check this. And x is xy. Let's check that this is true. So what is the norm of f? Let b squared. X plus 2y squared plus 2x minus y squared I'm trying to find a and b. I want to compare these with what is norm of x squared. It is x squared plus y squared. How to compare this? It can be done via Cauchy-Bonnikovsky-Schwarz inequality. Cauchy-Bonnikovsky-Schwarz inequality. By Cauchy-Bonnikovsky-Schwarz, less than or equal to 1 plus 2 squared times x squared plus y squared. It is equal to 5 times x squared plus y squared. Next, 2x minus y squared is also less than or equal to 2 squared plus 1 squared times x squared plus y squared. 5x squared plus y squared. And so it follows from this that the norm of f squared is less than or equal to 10 times the norm of x squared. And so this inequality is satisfied with b equals 0, right? I will rewrite it in this form. So we can, if we take a equals root 10 and b equals 0, then that equality will be satisfied. So this proves that since it can be done on the entire real line, this is true for the entire plane, right? Entire plane. So this is true for any t, any real t. So this means that the entire real line is the maximal interval for the solution of this initial value problem for any value of t0 and x0, y0. So I will omit the proof of this theorem then. I have no time to do this, but maybe it's more important to discuss these theorems with you. It is more useful, I think.